Good evening, everyone. Welcome back to our last session for the NPTEL course Metal Mediated Synthesis 1, which is being taught by Professor Divya Maitri from Department of Chemistry at Bombay, and I'm here to help you in solving all the questions or queries that you have. I hope you have enjoyed all the sessions so far that we have taught from week 1 to week 4. And today, since it's the last session, that I'll be talking about uh, some basic things. Like we can discuss that if you have any doubts, or otherwise, I have a final assignment which covers almost all the topics, so that it gives you an idea of what kind of questions are going to come in the exam, and that would also help you in revising all the concepts. So we will wait for a few more minutes for others to join, and after that, we can start with our final assignment session. This comprises of around like 70, more than 70 questions, which covers like shock or spawn catalase, carbon, their reactivity, different TT cross-coupling reactions, the Potkin reaction, which we have already taken yesterday, oxidative cyclization, and so other topics as well. And once we have discussed this assignment would be uh, shared to you, sorry, via that link. And these answers would also be given for this one. If you still feel any question or doubt, you can get back to us at any point of time. Moreover, in our yesterday's lecture that I was talking about some E9 cyclization, by mistake, it was written as ENZY, which pronounces as enzyme. So it is not enzyme, it's E9. So you can go back and correct that one. Sorry for that mistake. So yeah, this is all about our today's session. So we will wait for a few more minutes and then we can start. Thank you. So what we can do, since we have already taken the questions of Gaussian finite reaction and oxidative cyclization, so I am skipping those two sessions because the same questions I've put it, whatever we have covered yesterday, there could be some additional questions as well. So we will start with the CC cross coupling because this was been taken in like from week 2 to week 3. So just to revise whatever we have read so far. Okay. If time persists, then we can go back to section 1 and section 2. All right. So we have already talked about almost all the cross-cutting reactions, starting with Suzuki, Shimada, Kumada reaction, Nigeshi, Skill reaction, Sonobushida Heck reaction. So these are some basics, and then there would be some advanced questions. Okay, so the question number 21 says from section CC cross-coupling, the Suzuki, just a second. Okay. So Suzuki Miura coupling partners are typically aryl halide plus organothin, aryl halide plus organoboron, or organosilicon, organozinc. So we already know that Suzuki is basically for the aryl halides. This is generally the substrate for all the systems, but the main coupling partner for this one is your organoboron. So option B is correct over here. Similarly, moving to the next question, the Heck reaction that couples what? So Heck reactions, we know already that Heck reactions is a reaction between the aryl halides and the alkenes. So when it is being treated with alkenes and aryl halides like Rx plus some alkenes if you have, and then it would give you your another different type of alkenes. Like we have seen that it retains its trans conformation. So option A is correct over here. The next one, organometallic partner in stele coupling. We know that stele comes with the organotin, which was something like SnCl3 or whatever it is. So this would be the partner which would come and combine during the transformation step. So organotin is the right option. Moving ahead, Kumada coupling uses what? So we know that Kumada coupling generally involves RLI, RMGX. So both of them, they are normally they're called as organolithium, and this is organomagnesium halide. Generally, they are termed as Grignard reagents, where the nucleophilicity of your R is very, very high. They're highly nucleophilic. So the correct option is your Grignard reagents. So I hope this is clear. Moving ahead with the Sono-Kashira coupling, we if you remember that we have read about the head coupling and Sono-Kashira side by side, because this is the kind of two reactions which do not involve a certain metal or non-metal system. It involves just the alkenes and alkynes. Heck involves the alkenes, and Sono-Kashira is a reaction which would be for the aryl halide or alkyl halide or vinyl halide with the alkynes basically. So it works with the terminal alkynes and it would give you a new internal alkyne as the product. So option B is correct, which is between the aryl and alkyne bonds. Moving ahead to Hiyama coupling reactions, and Hiyama coupling reactions work with the organosilicon. So this is for the Hiyama. If I'm talking about organotin, so this works with your Stille reaction, organoboron. As I mentioned, that main reaction with their particular coupling partner is very, very important. Organoboron is Suzuki reaction, and organozinc is Negeshi, which is your followed up question. So this is correct. Similarly, Negeshi coupling reaction employs organozinc compounds, as we have already talked about, and organolithium comes into Kumada, organolithium or magnesium. Question number 28. In palladium catalyzed cross coupling, oxidative addition inserts palladium into what? So we know that we have a reaction of Rx plus some R dash and the coupling partner, be it boron, be it Sn, be it silicon or any other thing. So this first step would be that it is going to coordinate to palladium 0 and forming palladium R and X. So this is basically the CX bond, which is generally halide or the leaving group, ODF or iodine or bromine or anything else. So this is basically the oxidative addition of this particular moiety to the palladium, making palladium to go from 0 to plus to oxidation state. So next question that followed up is 29, which is in Suzuki coupling, the base primarily does what? So we have discussed this in full details in Suzuki. We are talking about that Here, boronic compounds are being used. So, for example, we have RbOH2. And if I'm using a nucleophile, that nucleophile transfers the electron to the B and it gets connected to there. Therefore, then this R minus, which is going to connect to your palladium, that becomes highly basic in nature. And therefore, the transmetallation steps become very, very faster. So, transmetallation more feasible, right? So if you say that Suzuki base does the palladium 322, that's not correct. Forms a pentavalent silicate. Firstly, in Suzuki, there is no silicon involved. That is anyway wrong, and pentavalent is not there. Forms a tetracoordinate boronate enabling transmetallation, which is correct because firstly that tricoordinated boron system would go to a tetracoordinated by involvement of a nucleophile at that base, and then it would help in transmetallation step. And the last is activates alkyne by deprotonation. Anyway, in Suzuki, alkyne is not the intermediate, the substrate and the coupling partner. So option C is anyway straight away correct, but you also need to see the other options whether there is a multiple answers can also be a possibility, right? So that you have to be very careful about. 30th question is a common catalyst for cross coupling that we already know that the above one is a Wilkinson catalyst, which is used for hydrogenation. FeCl3 is a normal salt, which can be used as a co-catalyst in some reaction. Nickel cord is a co-catalyst, but not generally in these cases. For cross coupling, majorly being used with palladium PbH3 4, where palladium is in zero state, or if we are starting with palladium +2, that gets activated to palladium 0 because palladium 0 is your active catalyst, which is going to be regenerated during the process, during the mechanism. So these 10 questions were about all the coupling reactions. The basic question like what is the requirement for this aryl, the RX moiety, and what is the requirement for that coupling partner, what is involved, like basically bases, acids, or certain conditions. That is the basic level of these questions. Followed by we have some advanced questions in section 4, which says that in reductive elimination from palladium 2 is accelerated by what? So whenever we are talking about the reductive elimination, it generally requires the two moieties. Say, for example, if I have this Ln and it is in +2 oxidation state and I'm having R and R dash. So if these two R and R dash, they should be cis to each other. So this kind of question is not here, like option is not here. And that would be accelerated if they're electronically rich and bulky because that would let them to go away from the palladium. If they are electronically deficient, they will take more electrons from the palladium and try to stay there. So that's why electronically rich and bulky ligands, they would tend to go out. That's why we increase the basicity of the R minus when it gets connected to the palladium. So for example, in Suzuki, just now we saw that in presence of the base, it enhances the nucleophilicity of that R minus, and then the transmetallation becomes feasible. And when that R and R dash are cis to each other, the electronic factor is very high, the bulkiness is there, that would definitely help in getting the reductive elimination step very faster. I hope this is getting clear. If there is any doubt, please let me know. So secondary alkyl halides prone to beta hydride elimination, and effective system is what? So we have already seen that, okay, this kind of system is not going to work for copper bipyridine. We have not seen that you can undergo this kind of coupling reaction. So that option is anyway out because copper is in plus that zero state with bipyridine. Palladium PPH, palladium phosphide, we don't really use it for alkyl halide until unless they're very bulky ligands. But for secondary and tertiary, nickel NHC, that N-heterocyclic carbonyls, they are very, very good catalyst for this one because palladium prefers to have the first primary structures and nickel can work for secondary and tertiary as it follows the radical pathway. If you remember that in our previous studies, in previous sessions, we saw that oxidative addition followed with palladium that is SN2 mechanism. So there would be an inversion. There won't be a radical pathway, but in nickel case, you get a radical pathway, which is very easy to be formed, and therefore it helps in getting these secondary alkyl halides getting into CC coupling reaction. So nickel NHC would be the right catalyst to be working with. Question number 33 is instellate coupling. Chemoselectivity in the presence of ARI or ARBR can be improved using what? So basically, generally, the stellate reaction is with the 10 compounds, but if there is if we have a aryl iodide or aryl bromide, so which one the chemical reaction is going to be happened with which substrate, that would be decided if we have a copper one co-catalyst that is named as Stille-Nigida reaction. So chloride irritants or high pressure of carbon monoxide is not going to help in either way. Only the presence of the copper one co-catalyst can help in that one. The next question is proto-deboronation of sensitive boronic acid is minimized by. So if we have a strong base at high temperature, if we have a copper co-catalyst, if we switch to organozinc reagents or using MIDA boronate as slow release partners. So for proto deboronation of sensitive boron as boronic acid, that becomes minimized or that gets affected if we are using N-methyl immunodiestic acid as slow releasing partners. So this would be the correct answer. In a substrate bearing aryl iodide or ArOTF, which one will generally go oxidative addition first to palladium zero? So ARI, that I has more leading property compared to the ODF. So ARI would be the first one. The major limitation of classical Sono-Kishida reaction is one, like whether it lacks the reactivity of the iodides, no. It forms a glazer type coupling via copper acetylide forming this diene. So what basically happens, like in Sono-Kishida reaction, we know that, okay, if we are using this copper iodide over there, so this copper X would react with your terminal alkyne, say for example this one, right? And you have a base over here, like NR3. It abstracts the H and forms this copper C triple bond Cr with NR3X minus, right? So this intermediate, this gets stabilized and this undergoes if we have say for example, 2 copper C triple bond Cr. So it would release your RC triple bond R and copper would be in zero state or copper would be in copper I. So in presence of the O2, like in presence of oxygen, it undergoes the homocoupling via copper acetylide formation. So this is the major limitation of these reactions. Preferred solvent for Negishi reaction, where we are using an organozinc compounds, it prefers to have THF or ethers because it can dissolve that easily. In Miyama coupling, where we are using silicon partners, they are typically aryl trifluorosilanes activated by fluoride. It's a trialkyl silanes. Without it, it is disiloxanes. Without base, are silyl enol ethers. So it's basically the aryl trifluorosilanes which gets activated by fluoride. In Shuji taught alkylic alkylation, soft nucleophiles tend to attack what? So we have when the allylic alkylation is happening, if we have a soft nucleophile, they would tend to attack more substituted terminus rather than the less substituted one. High pH in Suzuki coupling generally increases proto-deboronation of electronic for boronic acids because this is important really. That in high pH means like more basicity. And when more basicity is there, that would help in increasing the proto-debromination of that electron towards boronic acid. So option A is correct. Then we have photoredox nickel dual catalysis enable hydroformylation of alkenes, alkyl cross coupling oxidative addition or direct CH annihilation. So nickel dual catalysis can work with the hydroformylation of alkenes because the photoredox process. So the order of oxidative addition reactivity we just saw that I would be having comparably BR and OTF would be having comparable then CL. Moving ahead, which reaction is purposefully compatible with thioesters as electrophiles in CC coupling? So with thioester, we have seen that Negishi can work well because that is not applicable. Other Kumada reactions, they are not much good with the functional group because they can, if we talk about the Kumada versus Negishi, because in these reactions, these two things work. So this is less functional group tolerant because of the high nucleophilicity of organolithium, or we say Grignard reagent, where Negishi uses the organozinc compounds which are less nucleophile and therefore it can work with thioesters. An established water-soluble ligand system for aqueous Suzuki coupling would be BINAP PCY3. PCY3 is not having any charge over there, like it's a cyclohexyl group. Trisulfonated PPH3, BINAP is basically it's a binethyl group, and DPPF. So this would be the right option for working with the water-soluble ligand. Copper-free sonobutyrial reactions are often adopted to increase the oxidative addition rate, to suppress laser homocoupling and improve selectivity, avoid need for palladium, activates through organosilanes. This is anyway not correct. That we have seen that if we have a copper system, then it can undergo the homocoupling thing, and therefore uh, give us another type of alkyne, which is not the required for it. Okay, so that was all about the cross-coupling reactions. You can take a few minutes to undergo all these questions one more time, and then if you have any question or doubt, you can just ask. So we can start with our next section of the question. Okay, so section 5, shock osborne hydrogenation catalyst. So this shock osborne hydrogenation catalyst, we know that it is based on what? Rhodium, nickel, palladium, or ruthenium. We know that it is based on rhodium, so this is very straightforward. The catalytically active intermediate typically involves which species? So it actually involves a rhodium hydride species because that would help in hydrogenation step. Moving ahead to a characteristic ligand feature of these catalysts is monodentate phosphides, chelating diphosphenes, strongly basic alkoxides, or N-heterocyclic azides. So we know that it's a chelating diphosphenes, mostly a bidentate system that it uses. A classical asymmetric application introduced reduced nitroarenes or carbonyl alcohols, alpha acylamide acrylic acids to dehydroamino acid derivatives. So yeah, this one is correct. A key step in the cycle is beta hydrodeamination to give alkene, migratory insertion of alkene into RH H bond, single electron transfer to the substrate, or sigma bond metathesis to hydrogenation. So basically, the key step is basically the migratory insertion of the alkene into that RH bond. So this is very important. Upon oxidative addition of H2 to RH, the formal oxidation state would go to, since we know that it is Rn plus 1, it would go to Rn plus 3 because it is now connected to H and H. So it would go to formal oxidation state would change to plus 2 by plus 2, and that would turn from rhodium 1 to rhodium 3. So non-coordinating anions PF6 and VF4 are beneficial because they are they chelate rhodium and slow catalysis. They avoid strong binding at block sites. They provide hydride directly, or they oxidize rhodium 1 to 3. Any of these, if you can understand, these are only non-coordinating anions which are carrying a lot of space. So they actually avoid strong binding that block the sites. So option, this is correct. Followed by catalyst poisoning in rhodium hydrogenations can arise from. So it can arise whenever we are talking about the catalyst poisoning. So it can occur via CO coordination. So option A is correct. Now we have a general rate enhancement for hydrogenation, which can be increased or achieved by lowering the H2 pressure, by removing ligand, by increasing the hydrogen pressure where more hydrogen can be dissolved, and adding strong Bronsted acids. So basically, whenever you want to increase the hydrogenation, you have to have a high pressure of H2 if nothing is working. So that would help in dissolving more hydrogen into the system and make it more homogeneous and more prone towards the hydrogen to get the substrate to be hydrogen in there. So inertial selectivity in asymmetric rhodium hydrogenation primarily originates from catalyst counter ion identity, chiral pocket created by the chelating ligands, hydrogen pressure only, and stirring rate. Basically, like asymmetric means there has to be chirality. Until unless you have a chiral system which is coming from your either ligand or the catalyst, or you're adding a pre-catalyst over there, it can't create any asymmetry in your system. So chiral pocket or chiral symmetry has to be generated uh, by the relating ligands. So this was all about the shock Osborne catalyst. We have a section 6, which is Fisher versus shock carbene complexes. So which pairing is correct? This has been asked in question number 56. Fisher means late low valent metal with pi acceptors. Shock means early high valent metal with anionic donors, or other way around. Both Fisher and shock are electronically identical. Both require NHC ligands. So we already know that Fisher belongs to having a metal which belongs to late and having very low oxidation state. Generally, it's in 0 or +1. Since they are very electronically rich nucleophilic centers, so they definitely get pi acceptor ligands to stabilize them. Where on the other hand, the carbon center of the Fisher carbene becomes electrophilic in nature. If we compare it with the shock carbines are happening with the reverse trend, like metal is early transition metal with the higher oxidation state, making it electrophilic, and carbon center over there it becomes very neutrophilic in nature. So reactivity at the carbene carbon, Fisher is electrophilic, shock is neutrophilic, which is correct. If the metal is neutrophil in case of Fisher, the carbon definitely becomes electrophilic because there is a double bond over there. So you have to play in that regard. A typical stabilizing ligand set for Fisher carbene includes, so we know that in Fisher carbenes we have the pi acidic carbonyl groups or phosphide groups which are there for the metal set. Okay, so when you're talking about the stabilizing ligand, that means you're talking about the coordination with the metal system. If it is asking for like general groups, so you need to select what are being connected with the carbon centers as well. Straw carbons are mostly or commonly found in Brackel oxidation or alkene metathesis or hydroformylation or head reaction. They are generally being carbons are generally being seen in alkene metathesis reaction. A characteristic transformation of for Fischer carbons is 2+2 cycloaddition with alkenes, migratory insertion into MH bond, nucleophilic attack at the carbene center, and radical addition. So we have generally seen it's a nucleophilic attack at the carbene center because it's electrophilic in nature, so it can be easily attacked by the nucleophilic center. Moving ahead to So we have Krebs type ruthenium alkyl being carbenes, which are best described because in Krebs case also it's a ruthenium with a higher oxidation state, so it generally belongs to the shock type, but they are but bit better than shock carbene. Classical route of Fischer carbenes proceeds via alpha H abstraction, nucleophilic addition. One second. So a characteristic transformation for Fischer carbenes is migrating insertion into the energy. Okay, so the nucleophilic attack happens when we are talking about the a classical route to Fischer carbenes, like meaning we are talking about the synthetic process. So when a nucleophilic addition happens to a metal carbonyl followed by the alkylation that work, and in Fischer carbene, the in MH bond, if the insertion is happening, that works well. Stock carbenes are generated by protonation of a metal vinylidene. We have seen the synthetic process, so this one is correct. Fischer carbines typically show which spectroscopic trait. So very low carbon double bond frequency due to strong backbonding, IR inactive carbonyls, high field 13C shift or repair active. So they are generally IR inactive carbonyls. We don't see this kind of carbonyl stretching frequency in IR. So reaction with mineraloxide would most likely to occur at the carbon off plot. So since we are talking about this nucleophile, and that would only occur when the carbon is electrophilic in nature, and that works when we have a Fischer carbon. Now that was all about the Fischer and Straub carbene. Now we have the section 7, which is the last section, that is olefin metathesis. The key elementary step that initiates olefin metathesis is beta hydride elimination or 2+2 cycloaddition of MCr2. We have already seen that if we have Say, for example, R dash or the other molecule. So here it could be like metal center. So firstly, it would react with your uh, one metal center making R, R dash, and then it would tend to make a new M double bond something, and then therefore it would react, and therefore it undergoes a 2+2 cycloaddition of MCr2 with CC double bond, and therefore forms the metallar cyclobutane. A principal intermediate in the Jouvin mechanism is the pyrrollyl complex, or it's metallar cyclobutane. It's the same thing. Ethanolysis is driven by the formation of strong CF bonds or removal of ethylene from the equilibrium. Option B is correct. Arsine, which is the ring closing metathesis stem, typically gives cyclic alkanes, alkynes. When we are talking about the ring closing, it is definitely going to form a cyclic. It depends on what is the ring size, so it would give you cyclic alkenes. Relative functional tolerance is generally high for Strock carbenes, Grubbs catalysts, early titanium cobalt carbonates. If we compare the Strock and uh, Grubbs would be having more tolerance compared to the Strock one, but early titanium are having even more better. So titanium catalysts are the one which wins over here. The Frock and more CHR catalysts compared to drugs generally are more tolerant to protic substrates. So yeah, that is correct. They are uh, more tolerant to protic substrate. In cross metathesis, type 2 partners are typically highly electron-rich terminal alkenes, electron-deficient alkenes, tetrasubstituted alkenes, or cycloalkenes with the. So whenever we have a cross metathesis over here, so the type 2 partners would definitely be a highly electron-rich terminal alkenes that could help in undergoing that cyclometallation. Ring opening metathesis polymerization ring. So this you should know the full forms of many short acronyms. Ring opening, metathesis, polymerization. So it's basically primarily driven by relief of ring strain, radical stabilization, CO insertion, carbogrind. Definitely, it is for the ring opening metathesis. It's like radical is getting stabilized over there. Followed by we have last question, which is addition of vinyl ethers to ruthenium catalyst is often used to generate more active species to quench the catalyst via formation of a stable carbon, remove phosphenes, or increase the Z selectivity. So when we are talking about the vinyl ethers to addition to the ruthenium catalyst is often used to quench the catalyst via formation of a stable carbon. So this is the right option. And yeah, so this is basically the questions that we have covered. Similarly, we can see you can take few minutes to undergo these questions, then we can take the section 1 and 2 as well, which we have already discussed yesterday, but still it would be a recap for you guys. Okay, so the section 1, Poisson-Thorne reaction, where the Poisson-Thorne reaction is classified as we already know that alkyne interaction, then alkene, then carbon monoxide. So option B is correct, where first it's alkyne, then alkenes, then carbon monoxide. So 2+2, because that would undergo cycloaddition and CO. The pKr, the +1 component, as I mentioned, that it's carbon monoxide. The classical pKr is mostly commonly mediated by cobalt 2 CO that we have studied yesterday and the day before yesterday as well, the last week, sorry. The step often associated with the highest barrier in PKR is the alkyne coordination, alkene insertion, CO insertion, or the loss of CO2, CO6. So the highest barrier that is required is for the CO insertion step. Intramolecular pKa generally improve, meaning like you have alkene and alkyne same moiety that actually increases the regions like in which region that you want to go with. So option A is correct, followed by shorter tethers in the intramolecular pKa typically favor the formation of five-membered carbocycle, seven-membered, eight-membered cycloprotein. So we know that it's a five-membered carbocycle. In asymmetric pKa, the major stereochemistry is set during alkyne binding, cyclization, CO insertion, and reductive. In cyclization only, we see that we can tend towards okay, which product is going to be the major or asymmetry is generated. Then we have amine N oxides, which is basically having a positive charge acid behavior in PKR that promote the CO dissociation and association is very, very important. Activation to accelerate the turnover number. Electronic effects, PKR is generally faster when we have electron poor alkenes, electron rich alkynes lacking substituents or alkenes only. Whenever we have electron rich alkenes, that is even more faster for the PKR to work with. And the classical PKR furnishes cyclohexenones, pentenones, pentadieneones, or propenones. So it basically does the penteneones. We would be having a one double bond and then there would be a cyclic something like this. So one double bond and then you're done. The last section, the oxidative cyclization. A hallmark of oxidative cyclization is formation of a metallocycle intermediate carbocation, carbenoid or radical cation. We know that it's a metallocycle intermediate. During oxidative cyclization, the metal oxidation state typically increases by 2 units, decrease by -2, or remains unchanged or increased by 1 unit. Oxidative always involves a +2 oxidation rate of the metal state. Oxidative cyclization of an alkyne alkene pair is often catalyzed by palladium 0 phosphine, rhodium 1 phosphine, iron 3, porphyrin, or copper 1. So oxidative cyclization works with the rhodium 1 phosphine system. After oxidative cyclization to metallocycle, the most common next step would be when we know that oxidation has happened, the cyclization has happened, then the last step would be the reductive elimination of a system to give you the cyclized product. In and oxidative cyclization, the stereochemistry is mostly directed at metal alkyne coordination, metallocycle function. This is also same question made it in a different format. So yeah, because Poisson gun reaction is the type of oxidative cyclization, so that's why more or less it is having the same concept. For 2 + 2 + 2 cycloadditions, which metal is typically important for these type of reaction, where we already have a metal system which has a capacity to go from its lower oxidation state to higher, which is your nickel 0. That would be the best choice. Chelation by a directing group during oxidative cyclization generally lowers the barrier and enhances the reductivity or raises the barrier or suppresses the cyclization. Whenever you have a chelation over there, that actually suppresses the barrier. So the option A is correct. Compared to alkene, alkyl oxidative couplings, alkyne and alkyne oxidative cyclization are less prone to beta hydride elimination. They require external oxidants. They proceed via free radicals. They necessarily need CO. So actually, they are less prone to beta hydride because there is no option of beta hydride elimination over there. Oxidative cyclization of ene ions typically yields cyclopropanes, pentenes, or cyclopentenones, cyclohexanes directly or alkenes. So they actually does the option B. And the last question, US acid in oxidative cyclization frequently activate alkenes and improve cyclization rates, reduce the metal center, quench the metal cycles, and scavenge hydrides. So it basically activates the alkenes. That is what we were talking about the above, like where we are using the N oxide over there in the set. So yeah, this is all about the assignment that we have discussed so far. We have covered all the questions, around 74 questions. This involves like both easy to advanced level, and it would definitely help you in understanding and revising your concepts even better. So if you have any other question, doubt, please let me know in the comment section. So in the chat box, so that we will be able to help you.